So we resume this afternoon's session with Julia Kempe, and she will be talking about battling decoherence from quantum error correction to the 3-electron qubit. Thank you, Julia.
Thank you, and thank you, Michel, and the other organizer for inviting me. I took a bit more serious, perhaps, Michel's order to be pedagogical. So I will be covering, let me just go. I'll be covering quite a bit of work that is not my own work, but that, that gives you a slight overview of how quantum error correction is done. Most of this, or some of this, will definitely be known to you. I will use it as a basis to then go to work that I participated in, which are these last two chapters, Decoherence-free subspaces and Encoded universality. So I have to, disclaimer, admit, so most of this work in which I participated was done over a decade ago. However, and that also relates to the topic of this conference, a lot of this was taken up in the last, I would say, 5-6 years, and there has been a flurry of work using the basis of our work, related especially to small quantum systems and manipulating small quantum systems. So in that sense, the topic is perhaps not off topic, or not as much as I feared. I want to start and spend about a third of my time reviewing quantum error correction with you. And by the way, actually, all three parts of my talk tie in very nicely to Maziar's talk, the last talk before the break. So before I talk about quantum error correction, let me give you the motivation that people like me tend to have in mind when they look at this theory. And that is, of course, a quantum computer, which uses qubits instead of bits as the basic processing units, and puts the system in a superposition and tries to harness the power of quantum states and entangled quantum states to do computations that a classical computer cannot do efficiently. The dynamics of a quantum computer, of course, obeys the laws of quantum mechanics and hence is unitary. The readout in the end to get the result is a measurement. And it is well known that a quantum computer is at least as strong as a classical computer. So that is just the basic object. And quantum computing recently, actually, it has been always à la mode since I can think. But recently, there is a lot of new activity on the experimental side because a lot of industry has gotten involved into this. I mean, Google has a quantum computer, Microsoft has a quantum computer, IBM, Volkswagen, so you name it. There is now a lot of money, of industry money flowing into this, and a lot of new interest perhaps in the experimental development. What are the building blocks of a quantum computer? Building blocks of a classical computer, we think of them as elementary gates like NOT, AND, OR, NAND, and so on. A quantum computer has unitary gates, and it was established very early on that in order to perform any quantum computation or to simulate any unitary, we need 1-qubit gates. In particular, these two would be sufficient. These are rotations around certain axes, perhaps also flips. And for instance, a CNOT gate. That's not necessarily the only sequence that we need of gates, but that's one sequence that is known to be universal. So you get these, you get a universal quantum computer. And we'll see some difficulties with this later. And what is a quantum computation? So we start out usually, any algorithm that is, respects itself tends to start out by putting the state into some superposition of, say, classical states. So you can think of it as some parallel way of computation. And then, of course, in the end, to read out the result, we need to measure. And, you get a measurement with the probability proportional to the amplitude squares. The whole art of any quantum algorithm is, of course, not to measure right away, but to arrange things in a way that the bad results cancel out and the good results stay in place. So here, this is my cartoon version of Shor's algorithm, where you make sure that all the bad factors, or in this case, Fourier, it's some quantum Fourier analysis being used, but you make sure that the bad results cancel out, the good results stay, so that when you measure, you have a reasonable, constant, at least, probability to get the right result. So that's the whole art of any good quantum algorithm. And for that, you need to maintain the coherences. And in particular, you need to protect your quantum state against noise and decoherence. So how this is so the lofty vision of a quantum computer. In reality, we have the problem that is in the way of having a quantum computer today, and that is, of course, noise and decoherence. Moreover, not only do we have noise that affects the quantum states, also any way to manipulate them is fraught with errors. So our gates are faulty, and often we have only limited means to manipulate these quantum states. That's how it is, and that's what theory tried to mend to a certain degree. In particular, in the beginning, when people were, Shor's algorithm was already out there in 95. I think Shor did his work 94, even perhaps 93. There was a large amount of criticism, and it was a lot of, yes, maybe this is all great, but it will never work. In particular, Rolf Landauer, who was a very big critic of quantum computation, he was at IBM, said small errors will accumulate and cause the computation to go off track. And there is a certain point to it. Let us compare the classical and the quantum picture for this again. In the classical world, errors are discrete. You have these, in general, the model of a computer, you have these gates. What happens is that a bit gets flipped. It gets flipped or it doesn't get flipped. It gets erased, whatever, but it's a discrete thing. Here, of course, everything is continuous. So you have a multitude of errors. You have to deal with this. Error protection classically relies on redundancy, right? You want to make a code, you make it slightly bigger, you use redundancy to encode your information. Here again, the obvious problem, it's not a problem in the end, but what could be argued is how do we introduce redundancy if we cannot copy our quantum state when it's not known? To detect and to correct in the classical world, well, you look at the bits, right, and you do some operation to correct. You have some sort of error syndrome, you look at it and you correct. If you do the same in a naive fashion on a quantum state, you measure, there goes your, superposition. So you don't want to do that either. And classically, as I mentioned, what can happen? Well, the bit can get flipped, it can get lost. That's basically all that can happen. In a quantum case, as we have also seen in the previous talk, a bit can flip, a phase can flip, it can slightly rotate, a measurement can happen, all kinds of things can happen. What do we do? Lastly, classical computers don't actually face this fault-tolerant problem so much because gates are extremely reliable. In a quantum computer, gates are extremely noisy, and it's very hard to manipulate the information the way we want it. And then errors accumulate. Once you have gates that are faulty, you'll introduce more and more errors. How do we deal with all this? So let's first look at the quantum errors. There's many ways to describe them. You can look at them, describe them with the Hamiltonian operators and Markovian. It doesn't really matter. The model I'll use, which is equivalent to all the others in the end, is to look at it as a unitary evolution of a qubit in some environment. So the error in general is just some big unitary that happens to your encoded or to your qubit and to some state of the environment. And the assumption always is that we start out with a clean qubit that's isolated from the environment. And one can argue what happens if it doesn't. It's not the case, but generally let's assume that. Then the most general case, this is what will happen. We'll have some unitary evolution that will affect both the environment and the qubit. Right, I mentioned this. So what happens here is that we can, if you wish, we can write this error in some basis as, for general qubit, if you expand this, you get this type of expression. And in general, you can, of course, do some mathematics to just regroup the terms, if you wish. And then you'll get that the error is actually a linear combination of one of four things. Either nothing happens, or a phase flip happens, where, the phase of one gets flipped, or a bit flip happens, or both. Right? So this is just math. You can expand any error to be one of these four things in some coherent fashion. Right? So in that sense, we are already lucky because if we can deal with these four things, we are in business again. And the major assumption actually before I go on for error correction is that these errors are independent of each other. And this is an assumption that is not always true, and I'll speak to that in the second part of my talk. So, but given this assumption, and given the fact that mathematically an error is just, can be decomposed in this basis, we can now proceed and try to see how we can protect and correct for these errors. So let me just start with a simple example that is classical. When you have a bit flip error that can happen, the most naive way is to encode a logical bit into, say, 3 bits. So you just copy it 3 times, and then you're good. When you have a bit flip, you can just detect it because you know that if there's only 1 1, then there was a bit flip, right? And if there are 2 1s, then probably it was a 0 before. So if you assume only 1 error happened, then this allows you to decode the information again. Very simple. How can we use this quantumly? And what do you do when you have an error rate of epsilon per bit? You will be correct with this procedure exactly when only 1 error happened, 0 or 1. So if your probability initially of being corrupt was epsilon, you get it down to order epsilon squared, obviously. Quantumly, you can try to do a similar thing. So what we can do is we can try to copy our basis states. This is not violating the no cloning theorem because we're just copying the basis states. And the circuit for this could be, for instance, this one. So you can encode your qubits into such a state. That's possible to do. And then by linearity, your alpha 0 plus beta 1 will be encoded into this. So once you do that, then a bit flip error can actually be dealt with, even though errors are continuous and so on. If you just have a bit flip error, so if this is what will happen, then measuring the qubits will allow you to, if you do it the naive way, it will allow you to detect the error, but you destroyed the encoded information. Doing it slightly less naively, you can measure the parity of the qubits in a collective fashion without measuring each one separately. Right? You can just have a circuit that adds these two, measures. Say you want the parity of 2 bits, right? You just kind of add this to an ancillary qubit. This gives you the parity without distinguishing between, say, 0, 1 and 1, 0. And in this fashion, you can actually measure the parity without destroying the quantum state. So that's perhaps the second trick in this whole quantum error correction business. And so if you have a general bit flip on a qubit, here is the qubit alpha 0 plus beta 1. A bit flip can be modeled as going in one state and not doing anything, or with some, amplitude, square root of epsilon, flipping this bit. So this is just a unitary evolution that just flips the bit, right? Some rotation in that direction at that error rate. Then what you can do is measure the parity in this fashion that doesn't distinguish which qubit is flipped. And if you do it, and you get a parity that is odd, the parity that is either 0, 0, 0, or 1, 1, 1, if you measure this type of state, you will do nothing, and otherwise you will flip the qubit, the first qubit. So in particular, what happens is by observing this parity, you collapse the state of the error, which is some sort of coherent state, into either nothing happened or a bit flip happened. So you discretize the error by the process of quantum error correction in the quantum setting. That's very nice. And when you do that, you detect the error, you discretize it, and if need be, you correct it. So this again disentangles the qubit, the encoded qubit, from the environment. So this is a very nice trick to deal with the first 2 objections that we had, namely that errors are continuous and that measuring will destroy the quantum state. We have circumvented these 2 and found ways to, basically deal with these. So here, if you have this simple bit flip code, just like in the classical case where I told you encode 1 bit into 3, here we can do this with qubits and encode 1 into 3. And then there are 1 bit flip gives rise to all these possibilities here. With some probability, nothing will happen. And here are the probabilities that a bit flip will happen. And then there's 2 bit flips and more. And you can do these parity measurements. And when you do them, you get some sort of picture of, you do pairwise parity measurements. You measure the parity of the first 2 the second and the third, and the first and the third, and you get some pattern. You collapse the error, and you associate each of these parity patterns with an error. So for instance, the flip of the first qubit means you get this type of parity pattern, second and third. And then you correct back by just applying the right quantum operation. Okay, so this is very nice, and you also again get your probability of error down from epsilon to epsilon squared, like in the classical case. So we have done very well on the objections of Landauer that errors are continuous and will accumulate over time. We also have dealt with the fact that quantum states cannot be copied because we have cleverly just introduced redundancy in a different way. We also have dealt with the fact that measurement changes the state. We have used it to our advantage to collapse to an error or to no error. However, we haven't yet dealt with the fact that there is more than just bit flip in this world. And so the first code that was developed to deal with the general 1-qubit error was Shor's 9-qubit code, which was done as early as '96. And the way to do it is basically to concatenate 3 times the encoding that we have seen, roughly. So the 0 code word would be this one, and the 1 code word would be this one, and these 2 states are obviously orthogonal to each other. And bit flip errors we already know how to deal with, because this is the encoding we have seen. And with phase flip errors, what will happen is, for instance, on the first qubit, a phase flip error will translate to a minus sign here and a plus sign here. And what we can do in order to detect and correct this error is, instead of measuring the parity of the bits, we will measure the parity of the phases, so the parity of minus, plus, plus. So the parity of these 3 plus or minus signs. How do we do it? We observe that actually bit flip is nothing else than a phase flip in the Hadamard basis. So with a judiciously chosen rotation, we can turn a bit flip into a phase flip. And then we can just apply the same mechanism that we used for bit flips. Namely, we will transform the state, put it in a Hadamard basis, and then a bit flip changes basically the parity of the 3 qubits, even or odd parity. And putting it all together is, we could first correct for the bit flips, and then we go to this other basis. And here, this is the Hadamard basis. You can basically apply it here. I mean, with some math, you can avoid having all the Hadamards applied here. You can just apply them on the ancilla bit. And then you do some sort of parity measurement, say, of this block of qubits. And again, you get some sort of pattern that allows you to correct for this parity. So putting it all together means that eventually we have an encoding that allows us to correct for a general error, because we've seen that the error can be discretized. The error is anyway a linear combination of phase flips and bit flips. It can be discretized by the measurement, and eventually it can be corrected. And after Shor's original discovery of this 9-qubit code, which is a bit cumbersome, very long, there's been a whole flurry of activity which gave more generalized codes, where we could actually generalize classical codes to the quantum setting. And in that sense, the question was settled that you could correct T errors by choosing the appropriate code and reducing the error rate from whatever it was, epsilon to the power T plus 1. So you would only not detect, you would only be erroneous if you have more than T plus 1 error. And the way we encode the information is, we can think of encoding it in some sort of non-local way into the correlations between several particles. Now, unfortunately, we are not yet done, and this is the part where we kind of go beyond what's usually done classically. We are not done because we haven't really thought about what happens with our gates, which are also faulty. And how can we combine the faultiness of the gates with this whole procedure and still get the correct state. And also gates, meaning the gates you apply to a computer. I have here shown how to protect a state, but even the correction procedure might introduce errors, and the computation, of course, will introduce more errors. And then these errors will accumulate. So how have people dealt with this? For instance, here, if you have one error here, it would propagate to all of these 6 qubits and completely destroy the quantum state. So that's not a good situation, and we need to apply principles of fault tolerance. And luckily, these were already there is a classical theory of fault tolerance going even back to von Neumann or even earlier than that. Yes, so this is still making my point that we need to be a little bit smarter, because we not only need to store but process, and we can introduce errors. So there are principles of fault tolerance, and it turns out we can actually follow them by judiciously designing our gates and our codes. Operations should just not introduce more errors than the code can correct. It sounds like an obvious truth. And quantum gates need to be applied, obviously, to the encoded data. We can't just decode, apply the gate, and encode again, because that will subject our qubits to the error that we want to protect against. So all these things should not introduce more errors than the code can correct, and quantum gates should not introduce more than one error per block. Of course, shouldn't propagate errors, measurements shouldn't propagate errors, and should have a smaller error than what the code can correct for. All these are requirements, and they can be fulfilled. I'm just going to give one example. For instance, here I told you we have to measure the parity of qubit 1 and 2 in the very first example I gave you. And this is immediately prone to, this is not fault tolerant, because one error on the ancilla will propagate backwards and corrupt these two. But there are tricks. For instance, we can prepare the ancilla, the extra qubit that we use for measurement, in a state that doesn't allow us to learn more than just the parity. And then we can apply a circuit like this. And this circuit is fault tolerant, because each time one error will only propagate to one extra. One error here only propagates to, sorry, I'm overusing, to one extra qubit here. And so, we won't introduce more errors than we can actually correct. And so there are lots of tricks, and there's a whole, body of literature that is still, I believe, growing on how to do these things efficiently and nicely and in a way that it works out in the big picture. So it's possible, and there are transversal gates. I don't want to go into details. That's not the purpose of my talk. The message is that it is possible to do it, and we can deal with this very, with fault tolerance. There still remains one problem, namely that errors accumulate. So even if we do things fault tolerantly, we will still introduce one error every single time we do something. So we need to think about how many errors we can allow ourselves, because in the end, we want to do n gates. For some algorithm, you want to do some, say, n gates, and then your error probability goes with, grows with n, and we have to somehow deal with the asymptotics. This is not exactly manipulation of small quantum systems, but just bear with me for a second, just for the theoretical beauty of it. So we allow, fault tolerance gives us a failure probability that, depending on the code, if the code can tolerate t errors, correct t errors, our error probability will go down as epsilon to the t plus 1. But also, the recovery procedure will introduce extra gates, the coding, the decoding, the encoding, the redundancy. All this gives an overhead of, say, t to the a. I mean, not say, but that's the overhead. You have at least a linear overhead, usually more. And so when you do the math, you'll see that the failure probability scales as, not as epsilon to the t, but the term you have there is a t to the a, because you have to introduce, a linear, an overhead that grows with the number of errors that you want to correct. When you minimize this, you still get that your failure probability will be larger than this expression. And so when you open this up, you'll see that your errors, in order for this whole construction to work, your errors have to go inverse logarithmically with the number of gates that you want to apply. And that's not very practical, because here I'm being a theorist, and we're looking at, n being large, n at least growing. N is not just a constant. And of course, how can we make sure that our errors become smaller and smaller with the amount of computation we will do? We cannot. Our errors are intrinsic to the architecture, and they are given by some constant, whatever it is. But it's not something that will become arbitrarily small. Luckily, there is a way around this, and this is the last idea in the whole error correction part of my talk. We can apply some sort of hierarchy where we concatenate codes into larger blocks. So we will encode our qubits, say, into a 7-qubit code. Then we'll encode the 7 qubits into larger qubits, and so on and so on and so on. So we will open up, here are the actual computational qubits. We will encode them and then encode each of these qubits in turn, and so on and so forth. This, by the way, again goes back to von Neumann in 1956, when he was thinking of, working with components that can fail. in the context of synthesis of reliable organisms from unreliable components. So here we will simulate with this hierarchy, we will simulate our circuits, and per level, let's assume we have a one error correcting code, and we are able to correct one error, so we are able to go down from epsilon to epsilon squared. Then the next layer will go down from epsilon to the fourth each time we square it, and so when we have k such levels, our failure probability can be as low as this. Excuse me, it can be, it will be reduced to a number as small as this, and this number will decrease as long as we are below a threshold. So when you do the math, you'll see that as long as your error is smaller than some 1 over c, you will actually, reduce your failure probability and eventually make sure that your failure probability is smaller than the number of gates. So you want your failure probability to be smaller than 1 over n being the number of gates that you want to implement. And when you here now do the math, you're spared from this logarithmic decay that you otherwise face in your failure probability. And when you do this concatenated hierarchical approach, what turns out is that there is a threshold, as I mentioned, epsilon threshold, and if you are under it and it's a constant, you'll be able to correct for errors. And moreover, of course, you have an overhead, but this overhead only grows logarithmically with the circuit. So if your circuit unencoded would have n gates, now it will have n log n gates, which is not a drama. I mean, it's not even, it's not even n squared. You have overhead, but it's not a dramatic overhead. And of course, then when you actually, and there's, as I said, this is an active area of work to make theoretical constructions that have a high threshold. Because you want the threshold to be higher than what an experimentalist can achieve in his lab. And the early estimates were extremely low. So 10 to the minus 7 is anybody working with qubits in the lab will tell you this is not realistic. More recent estimates are as high as 3%. I heard even 5%, which means it's already something in the realm of things that an experimentalist might hope to achieve. And this way, all the obstacles have been basically eliminated, and we have this beautiful theory of error-correcting codes that allows us to deal with a world where noise is independent in attacking each qubit. Now I want to switch gears a little bit and talk about decoherence-free subspaces, because in error correction, the assumption that I made in the beginning, and that is always made, and that is also, by the way, a basis for a lot of criticism, is that the errors are independent and uncorrelated. This was crucial. It cannot be that the error is correlated and affects all the qubits at once. But what if that's not the case? And sometimes it's not the case. There are many natural setups where the error is actually correlated, could come as some larger mode in the bath or whatever. And in such a case, we're having trouble, because such an error can, spoil our nice theory of quantum error correction. So in such cases, and that's where the decoherence-free subspaces come in, for such cases, an alternative theory has been developed, which allows to protect against these errors. This theory with very different mathematics in it. So for instance, one of the prime examples is errors that couple here Pauli operators basically to the bath and effectively look like basically these large spin operators. So that's a very common error that is kind of collective and not independent. So how to deal with this? And the classical analogy again would be that the noise or the adversary, if you have say bits or coins, the noise would act in a way that flips either nothing or both. This could be our noise process. Think just classical analogy. Then what you would do is you would encode your bit or your coin into a state, say, of 2 coins by using parity as your encoding. So 0, 0 would be the 0 state, and 1, 0, say, would be the 1 state. And then your noise would keep flipping 0, 0 to 1, 1. But you would know that as long as the parity is 0, you are dealing with 0 and otherwise with 1. So this is a very simple classical analogy. When you go to the quantum world, something very similar. If you would have, again, such a noise process, you could again encode into such states here. And I mean, I'm writing the matrix because this is what becomes relevant later. You would have a noise that kind of acts in this space and in this space. And if you would choose this space as your encoding of 0 and this space as your encoding of 1, you would have an encoded qubit that is protected against noise. And I heard in the previous talk, we saw such a phenomenon where kind of dissipation, in this case, this type of noise, or not quite this type, but the spin type noise made sure that the qubit stayed in its state. So that's a related phenomenon. Anyway, so in general, you will have to look at basically the Lie algebra generated by these error processes. You'll have to look at irreducible, I'll spare you the math, but just give me one slide to see that the work wasn't trivial actually mathematically. You'll have to look at the irreducible representations of this Lie algebra, and you'll have to pick the right subspaces, like say this and this, to encode your information in a decoherence-free subspace. In a one-dimensional case, we have seen in the previous talk that the singlet is, for instance, unaffected by such noise, which is why Maziar could, using this type of noise, get his state back to the singlet. There are also the triplet states are protected by the noise, but yes, anyway. And for 3 qubits, we get the first genuine encoding of a qubit where we can use these, in the irreducible representation, we can use these 2-dimensional subspaces here to encode these. These are kind of identical copies of the same, operator in some basis. And we can encode our qubit into these spin half states, for instance. And then they will be protected against this noise. The problem remains, how do we compute within such a DFS? Let's assume we choose this as our encoding. It is protected against this error. We want to compute in this space without getting the qubit out of this space. And so it turns out that in this case, there is an interaction which is actually favored in solid state physics, quantum dots, and so on, which is the exchange interaction, the kind of the swap. And this interaction turns out, mathematically speaking, commutes with the error process. So you can apply it without getting your qubit out of that space. And so here I have switched gears. You look at it in a dual way. You look at the splitting of this Lie algebra, of this exchange interaction. You'll find these irreducible subspaces again, and you'll see that they generate the full SU2, meaning the full unitary group on this small component. So in short, the mathematical challenge, which I will spare you, is that if you develop this whole theory, what you have to do is look at the representation theory of these Lie algebras and find ways to encode in a way that you use the irreducible components, and in a way that you get the full SU2. Anyway, there's a whole, this is a whole big area of endeavor, but the short message is that in this case it's possible, and the exchange interaction turns out to be universal for these decoherence-free subspaces. And then what we did is we actually sat down and developed an encoding for these. We used this encoding for the 3 qubits and showed how to even produce a 2-qubit encoded operation, namely the CNOT, in a way that uses only exchange interactions, and it's possible. And we found these gate sequences of 19 operations to generate a CNOT on these encoded qubits. And you could also parallel a couple in parallel and not only use nearest neighbor interactions, then you get it down to less operations. You can also, you need 4 operations for 1 qubit or 3 for 1 qubit if you're parallelizing it. The whole point is that with this exchange interaction, you are able to compute inside this decoherence-free subspace in a way that is not taking the information out of this subspace. And the truth is that we worked on this decoherence-free subspaces for a long time, not thinking further, until one day I remember I was sitting with David DiVincenzo, I believe, and we were having coffee, and I told him, look, the exchange interaction is universal. And then I suddenly paused and said, oh, it's universal, meaning actually it is not known to be, in fact, it's known not to be universal in general. So the exchange interaction is something that preserves spin. We all know this. So in particular, it cannot be universal because it cannot take any state to any state. It preserves the spin. It cannot take a spin 0 state to a spin 1 state. So it was always discarded when experimentalists were having systems where they had the exchange interaction. They would always write papers where they would say, okay, we have the exchange interaction, we can do we can do some sort of computation, but unfortunately it's not universal. We also have to do 1 qubit gates or some other gate. That was kind of the paradigm at the time. And because we realized that we have a way of making this exchange universal, it was a big breakthrough. I don't want to praise this work. It was some sort of breakthrough because it gave the idea that if you encode your information, you can actually make interactions universal. So let's assume you are, I think I have a nice slide for this. Oh, wait, let me pause and just give you these sequences. So this is how these sequences would look like to implement a C-naught, for instance. But, I'm still, okay. So let me pause with this idea that we have over coffee and finish the decoherence-free subspace part. So these are subspaces that are invariant under certain errors. We can compute inside these DFS, as I've shown, for instance, with these 19-gate sequence. And so we have these two approaches to quantum error correction, the QHCC quantum error correction approach, which is active because you have to do correction all the time, but it has these assumptions of independence of errors. And here we have this passive kind of error avoidance tactic where we find subspaces of the system that are not affected by the noise, quiet subspaces. And that usually works with correlated noise. And we can actually combine these. There's, again, papers written partly by us, partly by others, to combine these two approaches to protect both against this and against that. Okay, so far so good. Let me get to this last piece of this encoded, the idea of encoding to make interactions universal. So as I mentioned, experimentalists go to great lengths to produce interactions that are considered to be universal. And we know that in order, in general, to have a universal gate set, we need 1 qubit gates and 2 qubit gates. And systems have preferences. Some systems have an easy time, for instance, doing single qubit operations, but a hard time doing 2 qubit operations. For instance, all the photonic setups, it's easy to manipulate a photon. It's very hard to make 2 photons talk to each other. However, in various other architectures, solid state or quantum dots and so on, several, it is actually easy to get 2 things to talk, have an exchange Hamiltonian, for instance, and it's much harder to implement targeted single qubit operations. So these architectures exist and they are quite widespread. Can we avoid these hard interactions? And here, as I mentioned, comes this, okay, it's a bit big word, but change of paradigm. Usually people, in order to build a quantum computer, they go to great lengths, they tweak the system to produce single qubit and C-naught or some such gate set. And what we advocated, and that took off, I believe, is that no, you can actually try to make do with what you have. Your system has certain Hamiltonians. There's even only one Hamiltonian, the exchange Hamiltonian. You can manipulate that well. Instead of going to these great lengths, encode your information in such a way that whatever you can do becomes universal. And with this exchange and interaction, we hit it to the heart, I believe, of what was done at the time. So here's again this exchange interaction, which is omnipresent everywhere in solid-state physics, but it is not universal. And on 3 qubits, here is a model. So here's the crucial idea that we use this encoding, which we have obtained from the theory of decoherence-free subspaces, forgetting about those entirely, just using the encoding, to allow for exchange-only universal quantum computation. Okay, so we encode the qubit into 3 qubits. That's the price we pay. But as a benefit, we obtain that all we need to do is apply the exchange interaction. And so this is the one idea that we put into this Nature paper that we wrote. And again, we had this gate sequence of 19 gates to apply a C-naught. Here are the sequences that could apply single qubit rotations depending on these tau 1, tau 2, tau 3, tau 4. And this was the general idea, basically. I want to say that there's a whole theory that we developed which people use less because these 3 qubits were already sufficient to do most of the things people wanted to. But I mean, if you really want to take it serious and develop this concept of encoded universality, you have to go through the language of Lie algebras. You have to see what you can generate. You don't have the multiplicative algebra, you only have the additive algebra, and so on and so forth. You have to really see what you do, and you can really prove rigorous theorems, but I'm going to spare you this because it's actually not needed for the small systems that we're currently looking at. Anyway, so the exchange interaction, so since we developed this in the last 5 years, and this dot, dot, dot is really a lot of dot, dot, dot. I mean, there are like hundreds of papers using mainly the they call it the 3-qubit exchange qubit. So this is the 3-qubit encoding that allows us to only use the exchange interaction to do any unitary operation we want. So this 3-qubit exchange qubit has been now applied and used and proposed in a multitude of architectures, mainly in semiconductors with quantum dots, with trapped ions. There's what people call the resonant exchange qubit, which again maintains, in this case, the encoding via the exchange interaction. There's a hybrid qubit, which is, I think, even implemented at the University of Medicine. 3 electrons shared between 2 quantum dots, and they use both charge and spin somehow to encode these 3 qubits, triple quantum dots, and so on and so forth. And here is one of these, illustrations. I just put it here, I guess, to, you're not supposed to, I mean, I left out the caption, but the point is people try to use 2 quantum dots to encode these 3 qubits in a way that they can really manipulate any exchange between any of these 3 qubits to implement any rotation they want. And then they could have 2 of these beasts, again, to see if they can't implement C0. So this is being done, and there is more and more papers on this subject, and I guess it's particularly timely because there are now more and more attempts to implement a quantum computer, and there's actually a lot of people opening startups and PhDs going directly into industry and getting a lot of seed funding to implement their favorite architecture, in particular these solid-state ones. There is another flurry of work. We came up with this 19-gate sequence of exchanges to implement a C0. More or less, we had to force ourselves. We just sat down and did some numerical optimization. And we didn't try to beautify it or anything. For us, it was more of a proof of principle that it can be done. So people have actually sat down and looked at these exchange sequences and at these gate sequences and tried to develop much. First of all, we showed that it works numerically, but people actually did it analytically using various theory Grosvenor bases, even analytical derivations, and so on. And again, there is a flurry of work. The dot, dot, dot really shows that people are dealing with this right now. And in particular, there are ways, for instance, to build these general controlled rotations using only interactions that involve very few. So for instance, you see here that there's no coupling between qubit 1 and qubit 2, which in some architectures might be very useful. And then the couplings here, the 1s and 3/2 and 1/2, are really multiples of, it's not like we had a very general sequence. I don't know where here it is. Here, our taus, these were our times. This is really ugly. We literally did numerics. People are now able to produce C0s with very simple, only 3 types of times, times of switching on these exchange interactions. So I guess 1 is probably a pi over 2 rotation, I believe, perhaps pi over 4. I think pi over 2. 3/2 is 3/2, half more, and 1/2 is half less. And so, again, these things need to be shown, and there's analytical derivations and so on and so forth. But in the end, there's more and more work on this and more work to make these sequences. Yeah, I'm actually already done, so make these sequences more amenable to experimental work so that they don't have to hit the, t equals 0.410899. And so that's a lot of work that's going on now, and that makes us very happy that our theory came to some use. So let me summarize what I tried to convey to you today. So I gave you some sort of, this was the pedagogical part perhaps, some sort of quick overview of what quantum error correction is. And let's face it, it can only work in the limit of many qubits. You've seen all this overhead that goes, and I write n times log n, but n times log n to the power a. This is a huge overhead if you think of what we can do today. What can we do today? Now you can log into IBM and you can actually manipulate their 5-qubit quantum computer that they have. Anybody can now, they put it online like a cloud. Now you have a 5-qubit cloud. They now have a better version. I just talked to talk to them. So they have now a better version where you have 16 qubits, which is very nice. It should come out very shortly. So you can literally go there to their website, design the gate sequence, any gate sequence you like, and you can manipulate 16 qubits. But I mean, here we're talking about, this was n log n, so this is a large n limit. So this whole theory is for the future, but it's not anything that will come about in the next 5 or 10 years. Because even for Shor's algorithm, right? Shor's algorithm becomes relevant. What do you want to crack? If you want to crack current credit card encryption, this is based basically on 1024 keys of length 1024. You will have to, you'll have to factor numbers of the order of 2 to the 1000. So, and for this you can make your calculation. You need tons of qubits. I mean, several thousands in the unencoded way, and then once you encode it with quantum error correction, it gets quickly to something close to 1 million, maybe. At least several tens of thousands. So this is not something that will happen even though we've heard of D waves already using thousands of qubits. This is not believed to be a true quantum computer, and for the true quantum computers we are at the order of 20. And what I hear from the experimentalists is promises that we get to the order of 50 in the next 5 years. So this is something for the future. But however, for these small systems, in particular architectures, for these small systems, we can harness the power of decoherence-free subspaces. They require a kind of a modest encoding, factor 3 or something. That's okay. And lastly, we can reduce the noise and the engineering challenges by using this encoding to make certain interactions like the exchange universal. So this is again relevant already to small quantum systems and hence to the topic of today's conference. So there is some, this is, I have to put this up, there is some, we are on the way in some ways to reconcile the lofty theory that we have and the experiment that we have with small qubits. This is kind of an attempt to bring these somewhat closer to each other. Thank you.
Thank you, Julia. Time for questions.
I was wondering about the exchange operations. So how does it work with the fault tolerance, for example? You need all these different angles of
So in the
swap.
case of decoherence-free subspaces, because the exchanges commute with the error process, each of them separately is keeps the, so first of all, each of them keeps the state in its subspace. Now what if they are faulty, you are asking me. So in that case you need to concatenate or something, or apply some.
Talking about if the angles is, for example, you need 3 over 2 and 1 over 2 and 1, if it's 3 over 2 plus epsilon,
right.
1 over 2 minus epsilon.
So then, the only answer I can give is that you will have to, in the end apply a layer of actual quantum error correction on top to deal with these things.
Okay, so you need to have each of these exchange qubits needs itself to be
right. Yeah, but again, these exchanges will keep the state in its protected subspace. They're commuting with this noise process. So at least in that sense, they are not doing anything bad to the information. But once they're faulty, once you over-rotate, it's not such a big problem because you still stay in your subspace. But if you're faulty in other ways, then you'll have to apply other means to stay in your space.
Other questions? I have one. So, is there any kind of classical analog of decoherence-free subspaces? It looks like not, but I wonder.
Well, the only one is the one that I, pulled along by the hair. If your noise process is such that it flips several bits at once, you can use parity type of encodings. But is this used anywhere seriously? Not that I know of. No, no.
Daniel?
Just a short remark. So there is a solution to get, say, a Pullman decoherence-free subspace. If you take a qubit, which is subject to low frequency noise, which causes dephasing, and you drive it with, say, just as you do for Rabi precession. And in the rotating frame, in fact, now your qubit is no longer subject to the low frequency noise, it's only subject to the noise at the Rabi frequency. So it's a Pullman decoherence-free subspace in some sense.
Poor man, because it's only part of the noises you're protecting.
Yes, part of the noise, but it's it can be quite efficient. But now, say coupling it to other qubits will be more complicated. But it's the same.
Yeah, I mean, as I said, I mean, in this general theory, we actually look at other noise models, in particular only partial rotations and so on. And indeed, there are ways to encode also in these scenarios. And in particular, your example is a very good one.
In the old times of NMR, this was called spin locking. Yeah.
Ah, spin locking, okay. Mm-hmm.
There are no more questions. Let's thank Julia again.